Can you tell what shape is inside this circle? If you can, awesome. If you can't, that's okay, because the difference in wavelength of light in these two is about 1 part in 500, which is roughly the lower limit of the frequency shift our eyes can see. We get different responses to different frequencies of light, but about 1 nanometer of change is as low as we tend to get. At least with our eyes, that is. But by taking advantage of how light interacts with liquid crystal, we can detect a change of 1 part in 500 quintillion, which is a billion times better than our eyes can do. To get a beam of light with this small of a frequency shift, we use what's called the Doppler effect. The frequency of light we observe emitted by a moving object changes depending on how that object is moving relative to us. A light source moving towards us has a smaller wavelength than one that's stationary, even when they're emitting the same frequency of light. When it's moving away from the observer, the wavelength gets longer. I won't nitpick the technicalities, but basically the peaks and troughs get compressed or expanded depending on how the light source is moving. So by sending a beam of light through a beam splitter and using a mirror to reflect one of the beams, we can change the frequency of light by moving that mirror. We also have the original frequency in the other part of the beam, so we can recombine the beams to detect a frequency shift. For context, this paper is based on a video by Umberto Bertolozzo, Stefania Rezzadori, and John C. Howell. John Howell is currently working on improving the results of the 2013 paper. Here he is to talk about his new experimental system.
What we have is a narrow band CW laser coming in through a fiber to this point. So this light is coming out of this fiber, and when it comes out of a fiber, it expands. So we have a lens placed about 75 millimeters away from where this fiber is letting the light out. And what that does is that lens collimates the light going out. This light then goes through here, and this is a combination of a wave plate and a polarizing beam splitter. And what this wave plate polarizing beam splitter does is it allows us to tune very carefully how much light we have going this way, which is just dumped, or this direction, which is going towards the interferometer.
What's really important about this setup is how much control we have over each factor of the light. The narrow band continuous wave laser basically means that it is quasi-monochromatic. It's essentially made up of one color. The laser power is turned down to less than 2 milliwatts, which is less than a standard laser pointer, and it's put through the combination waveplate and polarizing beam splitter, which allows us to control the polarization. With all of these factors, the power, polarization, and frequency of the light are all precisely controlled.
The light leaves vertically polarized, which means that it oscillates like this as it propagates towards the interferometer. When it hits this interferometer, then it splits in 2 different paths. And those paths are really important because they each play a unique role. Along this path, we take it through a quarter wave plate followed by a right angle prism. And what that right angle prism does is we shift it so that the beam coming back is slightly displaced relative to the beam going in. The reason why we use this optical trombone to cause a displacement was so that we could tilt this other beam back so that when they get to this liquid crystal light valve, they come in at an angle. Along this path, this is where the interesting stuff is happening. What we have here is called a piezoelectric actuator. And what it does is as we put in a voltage, we can put in an oscillating voltage, which will cause the piezoelectric actuator to move back and forth.
The back and forth motion of the mirror is what causes the Doppler shift, like I mentioned earlier, which is then what we're going to measure. For context, the mirror in the paper is being moved 100,000 times slower than our fingernails grow, which results in a detection limit of about 900 nanohertz. You may have noticed the silvery box around our new setup, which is our temperature control system. This is purely to calibrate and get as good of data as possible. When we move on to apply this system, we don't necessarily need that. It's going to be whatever the use case dictates. But the point is, we're moving the mirror tiny amounts. Again, slower than our fingernails grow, and measuring that Doppler shift.
Owing to the fact that we're moving these at such small increments, and we're doing it so slowly, the amount that red shift or blue shift changes, it's really small frequency changes.
Typical frequency shift detection works by overlapping the two waves and measuring their interference pattern. When two waves are on top of each other, the waves can cancel out in places and add together in places, which means they create a larger pattern. But when the frequencies are so close, you need a lot of the wave to measure the interference. We recombine our beams in a different way, using the unique properties of liquid crystal.
This is called a liquid crystal light valve. And a liquid crystal light valve uses liquid crystals to mix two beams non-linearly coming in at a very slight angle. Because when two beams come in at an angle relative to each other and they're coherent, which means that their phase properties are still preserved, then what you get is an interference pattern with peaks and troughs.
The liquid crystal light valve is a light-sensitive liquid crystal device. It's also a slow light material, which means the group velocity, that is the velocity of the interference pattern, is slowed down within the medium. The photosensitive properties of the liquid crystal light valve cause the refractive index of the liquid crystal to change depending on the interference pattern. That change in refractive index essentially creates a diffractive grating, which channels a specific amount of light from one beam to the other based on how different their frequencies are. The strength of the diffraction is directly related to the change in frequency, because it's dependent on the interference pattern, which is a result of the frequency difference. The wave mixing basically pulls some of the power from one of the beams and puts it into the other, by an amount proportional to the change in frequency. It's important to note that the combined power of the two lasers stays the same, but because we have a difference in amplitude now, we can work backwards to determine a frequency shift. From that frequency shift, we can work backwards to determine the speed of the mirror. A crucial element in this setup is what's called steep dispersion, which is the relationship we see between the change in frequency and the change in intensity. When we plot the frequency shift on the x-axis and the intensity shift on the y-axis, we get a graph that looks like this. And we can approximate the relationship between the two with small frequency shifts as linear. And the slope of that linear relationship is very, very steep, meaning a small change in frequency results in a large change in intensity. And the difference in intensity is quite simple to measure. We can use a ballast detector that essentially counts the number of photons in each beam of light.
What we have is one of the beams goes on one side of the detector and one of the beams goes on the other side of the detector, and it measures the power in one beam and it measures the power in the other beam. Then inside of this device, it takes the difference between those two powers, and then it sends out a signal that's amplified, that amplifies that difference between those two, that we can then measure and be able to back out how much the frequency changed or how much this piezoelectric moved.
It counts the number of photons on one side and the other and takes the difference between the two. If you want to know how else we use balanced detectors, check out our triangulation video, which is linked at the end of this one. In this system, as well as our triangulation one, a critical element in the system is making sure we reject as much noise as possible with the analog signal. Since we do our subtraction in its analog form, we retain as much information as possible, since environmental factors affect both of the beams of light the same. This technique is called common mode noise rejection, and it means we have a higher ratio of signal to noise. But what can we do with such a small Doppler shift measurement? Well, this system has already been used to make highly precise gyroscopes that can get instantaneous measurements instead of relying on an integration time. It can be used for the calibration of piezoelectric stages, or just monitoring of movement or vibration where putting another type of sensor is costly or difficult, such as hot, fragile, sterile, radioactive, high-pressure environments. Instead, we put a mirror, shine a laser into it, and get our result that way. Although this system is limited by being narrowband, it does provide tremendous accuracy and precision where it's applicable. If you have any applications for this kind of system that you can think of, don't hesitate to bring them up. Also, Dr. John Howell is working on refining these results even further with slightly different methods. So stay tuned for a future paper and video on these improvements. If you're interested in the technical details of the 2013 system, make sure you check out the paper linked in the description. And of course, stay tuned for future work. As always, if you have any questions or concerns, drop them in the comments below. I've been Patrick, this has been the Optics Lab, and thank you for watching.